Good morning, everyone. I'm Sarita Swanepoel, and today we're going to look at the basic principles of electrical circuits. Now, first we're going to look at current and potential difference because you need to know the difference. Now, when I look at current, I want to refer to your information sheet where you have that equation Q equals I times delta T. And then we want to rewrite that to become I equals Q over delta T. And now if you look at Q over delta T, that's going to tell you what current really is. Q is for charge in Coulomb and T is in time. So this is actually telling you that current is the amount of charge in Coulomb that is traveling through a point in 1 second. And when we are talking about per second, we're talking about rate. So it is the rate of flow of charge at a point in the circuit. If I have a reading of 3 ampere on my ammeter, that means 3 coulomb of charge is traveling past that point in 1 second. Now when we look at potential difference, for potential difference you have V equals W over Q. Now let's just quickly remind ourselves. W here is for energy and Q is for charge. So this will be the energy that is required to move 1 coulomb of charge per coulomb, right? For 1 coulomb. And that's why when you look at the definition, it is the energy that is needed to move 1 coulomb of charge, and that is between 2 points. So if you have a voltmeter reading of 4 volts, then obviously that voltmeter is telling you that 4 joule of energy is required to move 1 coulomb of charge between those 2 points. Now with current, I usually find it easiest to think about a hose pipe with a lot of marbles inside. The charges are already there. The cell is not adding the charges to the circuit. The cell is just providing the energy, it's pushing them along. When we want to measure current, we are going to measure that with an ammeter. And an ammeter you are always going to connect in series because an ammeter is going to measure at that point in the circuit. It's the rate of flow at a specific point in the circuit. So you're putting it right in there in series. But when you are measuring potential difference, then usually you have a resistor there and we are connecting that voltmeter in parallel over that resistor. Because this voltmeter needs to measure the energy, but the energy needed to move 1 coulomb of charge between 2 points. So what this voltmeter is actually doing, it's catching 1 coulomb over there and we are comparing their energy before to their energy afterwards. So it's telling you how much joule is needed to move that 1 coulomb of charge from that point to that point. So that is your potential difference. Remember, all meters must just measure. They're not supposed to influence the circuit. They're not supposed to change anything in the circuit. So when you use an ammeter that is in that circuit, we are going to use an ammeter with a 0 ohm resistance. It's not going to require energy to go through that. It's not changing the currents. It's not changing the potential difference, right? It's just measuring because it has no resistance at all. But when you get to a voltmeter, remember for a voltmeter, we don't want the charge turning off and sidestepping and not passing through that resistor. We want them to stay in the circuit where they were supposed to. So here, when you look at a voltmeter in parallel, for that voltmeter, we're going to use an infinitely big resistance. That is the symbol for infinity. So a voltmeter has an infinitely or a very big resistance, which means when the charges arrive over there, nothing will choose the bottom pass because the resistance is too big. Every single charge will pass through the top. Right, guys, and that gives us a way to work with voltmeters. If there's a voltmeter in the circuit and you are confused because it's very busy, you can ignore that voltmeter because no charge is traveling through that voltmeter. Now we want to know what's going to happen to current and potential difference when we are in series and parallel circuits. Now when things are connected in series, it means they are connected one after the other. The charges have to pass through the first one and through the second one. Now remember, we're thinking about a hose pipe with charges inside, marbles inside. Now, every single marble there can just move if the one in front moves, which can only move if the one in front of that moves. So that tells me if 3 coulomb of charge is passing this point in 1 second, then there we also have 3 coulomb of charge passing in 1 second. They can only pass if the one in front is passing as well. So that is telling us that the current is the same everywhere in the series circuit. It doesn't matter if we're before or between or after resistors in series, the current will be the same everywhere. There's nowhere for charges to leave this wire or to gain access to this wire. What's there is going to stay there, and they are going to move at the same speed. Potential difference is all about energy. So if you look at this series connection, the V1 over there is measuring the energy used in the first resistor. And remember, used here is just converted to something other than electrical energy, like heat energy. So V1 is measuring how much energy is converted in that first resistor. And V2 is only measuring the energy used in the second resistor. So V total over the whole series connection is going to be V1 plus V2. Charges can't choose, they have to go through both. In parallel, if you've got 3 coulomb per charge arriving over there and 1 coulomb per second is choosing the top part, that means the other 2 coulomb should choose the bottom part. So that always tells you the total series current is just going to be the top and the bottom added together. And when we get to potential difference, remember that's all about energy. The total energy used at the top is going to be the same as the energy used in the bottom. You can see that if you look at the points where the voltmeters are connected before entering that parallel. Can you see all the points where that voltmeters are connected have the same energy on this left-hand side? No change in energy between those 3 points. But the same is true on the right-hand side. No energy change between those 3 points. So they're all measuring the same change in energy. The potential difference over the whole parallel combination is equal to the potential difference over the top branch is equal to the potential difference over the bottom branch. Right, next we are quickly going to look a little bit at Ohm's law, but we're still going to focus in a whole video on that one. Now, if you look at Ohm's law, R equals V over I, that is going to give you the relationship between the potential difference and the current. Now, in Ohm's law, the potential difference is directly proportional to the current in the conductor. And there's just one qualification. It needs to be at constant temperature, because only then is the resistance going to stay constant. Now, what I want to talk about here is when you're using R equals V over I, it's very important that you use the right values. You can either add the values for R, V, and I for a specific resistor, or for a specific combination of resistors, or for the whole circuit altogether. Say, for instance, you had a circuit and you had a 12 volts over there, and they asked you to calculate the current in the 8 ohm. Now, I've got R equals V over I. I've got the R over there, 8. But that 12 volt is for the whole circuit. That 12 volt is not true for the 8 ohm. So I am not allowed to use the 12 with the 8. If I want to use that 12, I will have to get the total resistance of the circuit first. So I will have to add them together, and then I'm going to use R equals V over I, not for the specific resistor, but for the whole circuit. And then, since the whole circuit is in series, it doesn't matter where I'm asked for the current, it will be the same everywhere. Now we are going to talk about EMF. Now, EMF is just a specific potential difference. Now, for potential difference, we said that's energy to move 1 coulomb of charge, a unit charge, and the only thing that's new is the EMF is the voltage, the potential difference that's supplied by the cell. So if the cell supplies that potential difference, we call that the EMF. All the energy that is supplied by the cell will be used in the circuit. If you have a circuit like this and the cell is supplying 12 volts, that means if this one is using 8, then that bottom one will be using 4 volts. So guys, that was the basics, and now we are going to go on to apply that basics to voltmeters and ammeters in the next video.